Okay, so we are going to look at the introduction to aromaticity and try to answer the question, what are aromatic compounds? Why are aromatic compounds as stable as they are? Why do they deserve our attention? And first of all, the first aromatic compound that was identified was benzene. And we knew that the formula of benzene was C6H6. And if you look at the molecular formula of benzene, and you try to work out the number of HDIs, you compare that to C6H14, so it means you're missing 8 H's, and that would imply that you had 4 HDIs. So there are 4 indices of hydrogen deficiency, 4 double bond equivalents, and so on. And for the longest time, it confused organic chemists what the structure of benzene was. Some people thought perhaps it would have had 2 triple bonds, 4 double bonds, a ring and 3 double bonds, and there were a whole number of possibilities. In the end, benzene was identified to have a structure that we write like this, and this is called the Kekulé structure of benzene. Now, this really consumes all 4 HDIs, right? It's got a ring and 3 double bonds. But we realized very soon that this can't be right, because if benzene had this structure, then I would expect to have 3 short bonds, because the double bonds will be short, right? So 3 short bonds and 3 long bonds. So benzene really should have alternating short, long, short, long, short, long bonds. And you can tell from the physical structure of benzene, the benzene molecule, that that's not true at all. And what some people said, what Kekulé was suggesting, was that the benzene molecule, in fact, was equilibrating between that structure and this one, and that it was happening too quickly to be detected. So we know that's not true, right? We know now, in fact, that this is better represented as a resonance arrow, so that the resonance forms of benzene are such that benzene perhaps can be represented better by sort of a delocalized sextet of electrons. But let's look at this Kekulé structure of benzene again. A compound having this large number of degrees of unsaturation and only having 1 ring, you'd expect benzene to behave in a certain way. So if in fact the Kekulé structure for benzene was correct, I'd expect that if I treat benzene with, say, bromine, that benzene would add, right? I would expect to see the formation of, at the very least, maybe we get addition of bromine across 1, if not all, of the multiple bonds. But I don't see this reaction, okay? You know that double bonds also decolorize potassium permanganate. I don't see that either. And so benzene doesn't give the type of reactions that we expect it to do. It doesn't add the way we expect compounds that are highly unsaturated to add. It turns out benzene will in fact react with bromine in the presence of iron. So if I use bromine in the presence of iron, I do end up getting a product, but the product, surprisingly, is this one. So what we get is a reaction with iron as a catalyst, and the product of the reaction is not addition, it's actually substitution. So benzene really behaves in an unusual fashion. It is highly unsaturated, but it reacts not by addition, but in fact by substitution. And the substitution depends upon the presence of a catalyst. It turns out iron is the prerequisite to the catalyst. What actually happens is that iron reacts with bromine to form the actual catalyst in this reaction, which is ferric bromide. And we talk about that in some more detail in a second. So at the very beginning, benzene, which we identified to be aromatic, was called aromatic because it had a smell, which is a silly thing, because almost all organic compounds have smells anyway. But then the term aromatic began to morph to be aromatic compounds are those that are highly unsaturated, but do not react by addition, as what you might expect for alkenes and alkynes. In fact, they react by substitution. And that substitution depends upon the presence of a catalyst. Okay, so the question then is, if the reaction, if we can force the reaction to go, but when it does, it reacts by substitution, it means there must be something inherently stable about the benzene ring. There's something inherently stable about this arrangement of pi electrons, that the system is trying to protect it. It doesn't want to add because somehow that would disrupt this aromatic sextet. So the question is, what is so special about benzene? Right? Why does benzene resist reaction? And if you force it, the reaction will give you, rather stingily, a substitution. A substitution that basically protects the integrity of the aromatic sextet. So we're going to ask two questions. One, is there something special about the sextet? And is that unique to benzene or benzenoids? And the other question we're going to ask and answer right now is, how else could we demonstrate this unusual stability of the benzene ring? And let's answer the second question first. It turns out that if you guys remember from your organic 1, that it is possible to look at the relative stabilities of, for example, alkenes, right? So you may remember that if I have, let's say, 1 butene, and I look at, say, trans 2-butene, say cis 2-butene, and then trans 2-butene, all of these compounds can be hydrogenated to butane. And if I measure the delta H of hydrogenation, what I find is that the delta H of hydrogenation, in other words, the energy released when I hydrogenate a mole of trans 2-butene to form butane, that number is less than the delta H of hydrogenation for cis 2-butene, and that number is less than the delta H of hydrogenation for 1-butene. Now they all decay into the same product. And so the fact that the delta H of hydrogenation for 1-butene is the greatest means that it must have the greatest amount of energy, right? So it releases the most amount of energy as it decays into butane. So from the relative values of the delta H of hydrogenation, I can determine the relative stabilities of the alkenes, right? The one that has the greatest amount of energy that is released is the one that has the highest amount of energy to begin with. Okay, and if you want to do it this way, if I'm going to drop this marker to the table, and I'm going to put the marker at 2 different heights. So if it drops here, I can hear some amount of noise created. But if it drops from here, more sound energy is released because it's falling from a greater height, right? It has more energy to begin with. So that the energy released on decay to the same level, and this decay is falling. In this case, the decay is hydrogenation. The energy released is a measure of how much energy I had to begin with. So the higher I am, the more energy I release. The lower I am, the less energy I release. So we can do something very similar with this system. So I'm going to take cyclohexane, and I'm going to decay compounds to the level of cyclohexane. And what I'm going to start with is, say, cyclohexene. And what I find is that when cyclohexene decays, when it gets hydrogenated, let's say the delta H of hydrogenation for cyclohexene is some number x, right? Let's just call it x. And it's a kilojoules per mole. If I take the unconjugated cyclohexene, so I take the 1,4 species, and I hydrogenate this one, well, this value is pretty much 2x. And that makes sense, right? It's X that hydrogenated one double bond, and so I'd expect it to be 2X that hydrogenate two double bonds, and are unrelated. On the other hand, if I were to try to hydrogenate the conjugated cyclohexene, so in other words, if I were to try to conjugate, to hydrogenate this species, right, so the 1,3 cyclohexadiene, I find that the energy released is some 2x minus y. So this value is y. And I can argue that very simply and say, well, the conjugated species is more stable than the unconjugated one. And we've been preaching that since Organic 1, that conjugation stabilizes because the p orbitals can interact with each other over a wider system. And so I could call y the resonance energy, right? That's the stability that I'm conferred based upon resonance. So the question then is, where would benzene go? So if I put a third double bond in, and I'm looking at the so-called Kekulé structure of benzene, where would I expect benzene to be? And I might say, well, maybe I'm going to start with 3x, so maybe somewhere here, and maybe there's lots of resonance in benzene, so maybe it's 3x minus y or 2y or something. It turns out, so let's put this number here as 3x, right? And that might be where we'd expect benzene, cyclohexatriene to show up, right? That might be what we expect to show up. Or maybe somewhere here when you add the resonance energy. It turns out that actual benzene, which I will draw like this for now, this is benzene, actually shows up even below the value for this species. So benzene is a heck of a lot more stable than we'd expect it to be. And this is not accounted for just by resonance. There's something unusual with benzene that exceeds normal resonance, which explains why when you treat benzene with bromine, first of all, it refuses to react, right? But if you force it in the presence of a catalyst and heat, it will give a reaction, but that reaction preserves the aromatic nucleus. So what is so special about benzene? And that brings us to the issue, which is the second question we asked. Is this stability, this aromaticity, is this unique to benzenoids? And the answer is no. It turns out that there are certain conditions that are required for species to be aromatic, and that aromaticity is not localized to benzenoids. And so I might call this stability, I might call this aromaticity, right? Aromaticity or aromatic stabilization. So benzene itself is much more stable than what I'd expect cyclohexatriene to be, okay? So what are the conditions for aromaticity? So one, the species has to be cyclic, it has to be planar, it's a flat molecule. It must have a contiguous pi system. I'll explain that in a second. And it must also have what's called a Huckel number of pi electrons. So there are 4 conditions for aromaticity, and we're going to explore those looking at benzene as our model, and then extend it to other species. Okay, so it has to be cyclic. Well, that's fairly straightforward. Benzene, as we know it, is a cyclic compound. It has to be planar. So what this means is that the entire molecule must be flat. So if I were to take benzene and turn it on its side, and this is not going to be a great diagram, but what you'd expect to see is something like this, right? So these are coming out of the board, right? And I'll have a p orbital in this carbon, p orbital here, p orbital here, p orbital here, p there, p there. And in order for the p orbitals to overlap sideways, which I need for the pi bonds, the entire assembly has to be flat, so that all the p orbitals, right, can line up to overlap. So in order for me to get all the sp2 hybridized carbons and their associated p orbitals, lined up appropriately, the system must be flat. So for benzene, I can check those first two. We're cyclic and we're planar. It must have a contiguous pi system, and what that means is that the p orbitals, we'll say p for now, there's a difference we'll add later. The p orbitals have to be in contact. So we tend to think of the United States as having, so Hawaii, which is a state, is not contiguous with the US. It's not in physical contact, right? So all the states are connected by land masses except for Hawaii. But so in benzene, all of my p orbitals, right, are adjacent to each other. And so this is a contiguous pi system. Now, I'm going to point something out here as well. If I look at this pi system, what I see is that the p orbitals can overlap at the top and at the bottom. And so in many ways, when you look at the benzene ring, I can see this as a pi cloud that extends above and below the plane of the molecule. So of course I've got my CHs, right, that are here. So CHs, and I've got a CH coming onto the board here, and one going back into the board, and so on. And I can imagine then that the carbon-hydrogen framework is like the patty of a burger, and the pi cloud that extends above and below it, that represents the bun. So in some ways, the benzene ring is a hamburger. They're the buns which are made up of the pi cloud above and below the patty, which is the CH framework. And because of this sort of this pi cloud, that is one of the reasons why the benzene molecules are often drawn as a circle in the middle. The circle indicates the aromatic nucleus, the 6 electrons, and it also indicates that there is a pi cloud above and below the molecule. Okay, so we've got cyclic, planar, contiguous pi system, and then the other issue is I must have a Huckel number of pi electrons. Okay, so what is that? So a Huckel number, and the best way of doing it is to say it's a 4n plus 2 number. So in fact, I'll give you some of this. So if n is 0, 4n plus 2 is going to be equal to 2. So 2 is a Huckel number. If n is 1, 4n plus 2 is equal to 6. So 6 is a Huckel number. If n is equal to 2, then 4n plus 2 is equal to 10. So 10 is a Huckel number. So a system having 2, 6, 10, 14, 18 pi electrons will have a Huckel number of pi electrons. Okay, I will just point out that Huckel number is a number that comes out of the quantum mechanics. Okay, just a solution to a quantum mechanical question. But if a system has all 4 characteristics, it is going to be aromatic. So why is benzene aromatic? Because it's cyclic. It's planar, which it must be in order for the p orbitals to overlap and form the pi system. It has a contiguous pi system, and benzene contains a Huckel number of pi electrons. There are 2, 4, 6 electrons. 6 is a Huckel number, and therefore benzene has all of the features of aromaticity. So benzene is aromatic. It's unusually stable. What other species are aromatic? Well, I'm going to put a couple on the board, and let's explore if these are aromatic. So let's do this compound. 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 Let's do this compound, the species. So that one. Let's do this one. And let's do this one. Okay, so we're going to try to examine, we're going to test each of these through the lens of the 4 conditions for aromaticity. Let's start with this one. Is this aromatic? Well, is it cyclic? No. So end of story. This compound is not aromatic. What about this one? Well, it's cyclic. That's good. Is it planar? Well, 1, 2, 3, 4, 5 are going to be in the same plane because I've got p orbitals on this carbon, that one, that one, that one, and this one, so those will still be in the same plane. But that carbon is sp3 hybridized, so that one will pucker. So this is not planar, although it's cyclic, it's not planar, so therefore it's not aromatic. It also turns out, so that's enough of a disqualification, but it also turns out that it does not have a contiguous pi system because I've got P, 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 but there's no p orbital available in this carbon. So it fails that test as well. It just needs to fail 1 not to be aromatic. So I'm going to cross that one out, that's not aromatic. This compound is called naphthalene. This is what's found in the old version of mothballs. And if I were to look at it, is it cyclic? Yeah, now bicyclic is cyclic. So it's cyclic. Is it planar? Well, yes, it'll have to be if all of these p orbitals are on adjacent carbons, right? So there's p orbitals on all of these carbons, so they will orient themselves to be planar, so the p orbitals align and overlap sideways. So we're cyclic, we're planar. We definitely have a contiguous pi system because there are p orbitals in every one of these carbons. Does it have a Huckel number? Well, it's got 2, 4, 6, 8, 10. 10 is a Huckel number, so naphthalene is aromatic. So what I'm going to do is I'm going to redraw naphthalene to indicate aromaticity, and I do that with a circle in the middle. So that's commonly how you see naphthalene drawn. Let's look at this compound. So is it cyclic? Absolutely. Is it planar? It has to be for all the p's to overlap sideways. Does it have a contiguous pi system? Absolutely. P, 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 all the way around. Does it have a Huckel number of pi electrons? Well, let's check. 2, 4, 6, 8, 10, 12, 14. If n is equal to 3, then 14 is the 4n plus 2. So this compound is aromatic. It's called a crown ether. It's actually called 14 crown ether. So I can redraw the species like this. And again, the circle in the middle is an indication that the species is aromatic. Is this aromatic? This compound is called pyridine. So is pyridine aromatic? Well, let's see. It is cyclic, it's planar, it clearly has a contiguous pi system. But if I look at the last question, how many electrons does it have? It seems to have 2, 4, 6, and then there's a lone pair on the end. And the question is that lone pair part of the pi system? So I'm going to go back and look at the structure of benzene that I had on the board. So the only difference between pyridine and benzene is that this carbon H is not here. What I have instead is a nitrogen. There's a nitrogen atom here, and that lone pair is here. So what this means is that this lone pair is not part of the pi system. It's perpendicular to it. Right? This lone pair, this sp3 hybridized orbital, or sp2 hybridized orbital, is pointed in the plane of the molecule. The p orbitals are perpendicular to it, so they don't overlap. If it doesn't overlap, it's not part of the pi system. So really, I can't count that. So if I look at pyridine, pyridine then meets all of the checks. It's cyclic, planar, it's got a contiguous pi system, and a equal number of pi electrons. This is not counted. Which means pyridine is basic, because that lone pair is available, it's not tied up in resonance. So I can redraw pyridine now like this. And pyridine is the first of what we call the hetero-aromatic compounds. It's a hetero-aromatic compound, meaning that it's aromatic, but it has more than one type of atoms in it. In this case, carbon and nitrogen. This compound is called pyrrole. And the question is pyrrole aromatic? Well, it's cyclic, it's planar, and it's got a contiguous pi system. Now let's be careful about this. If I look at the structure of pyrrole, so I'm going to erase this. If I look at the structure of pyrrole and I draw resonance forms for it, right? I can show, for example, that that lone pair of electrons in the N is actually involved in resonance with the rest of the system. Right? I can move this over, blah, blah, blah. So what I might have called a lone pair here really isn't. It's part of the entire pi system. Why is it that I'm considering this lone pair as part of the pi system, but I didn't this one? I explain why this one could not be, because it's perpendicular to the plane. Let's look at the structure of pyrrole and see what's happening there. So I'm going to turn pyrrole on its edge and try to draw that structure. Turn pyrrole on its edge and try to draw that structure. So here are my p orbitals on the carbons. The nitrogen has a lone pair and an H. And it has a choice. Either it can put the H up and put the lone pair that way, that's one option, or it can put the lone pair pointing up and the H pointing out. Now each of these p orbitals has one electron. So it is the nitrogen's advantage to have the lone pair pointing up. So this way I have 1, 2, 3, 4, 5, 6. So when these overlap, I get my sextet. I get the 6 electrons, which is a Hugel number. So that lone pair of electrons in the pyrrole is part of the pi system, which is interesting because while pyridine is basic, pyrrole is not. Because this lone pair is not available to an attacking acid. It is locked up in aromaticity. And aromatic compounds will be reluctant to lose those electrons because that means losing aromatic character. And I will point out that aromaticity is, to organic compounds, what a noble gas configuration is to elements. Elements will bend over backwards to get a noble gas configuration. That's why they react. Organic compounds will bend over backwards to obtain aromaticity. Aromaticity is at the bottom of the energy well, a very, very stable species. So pyrrole is another heteroaromatic, and I'm going to draw a circle through it. This compound is called furane. It's spelled furan, but it's pronounced furane. And as you might guess, furane is going to be aromatic. It's cyclic, planar, contiguous pi system, because I can replace the O and show the electrons moving around and so on. That lone pair is going to be here. Right? If I draw furane, that lone pair is going to be, one will be in the plane of the other p orbitals, one is perpendicular. So I don't count this one. So I'm left with the 1, 2, 3, 4, 6, which is a Hugel number. So furane is another example of a heteroaromatic. Let's look at this one. This is called the cyclopentadienyl anion. Right? So it's cyclopent, and it's got 2 double bonds. So it's a dienyl and it's an anion. Is that aromatic? Well, It's cyclic, it's planar, which will have to be because this negative charge is in resonance with the rest of the ring. That should look very much like this. So there is, I can draw a p orbital here, and they'll have to be in plane for that process to occur. It's got a contiguous pi system, therefore. And how many pi electrons do I have? Well, I've got 4 in the 2 pi bonds, and that minus charge really is a lone pair of electrons. So in reality then, I've got 6 pi electrons in this anion. So it means then I can redraw the cyclopentadiol anion like this. And I'll put a negative charge. This is an example of an aromatic anion, or an aromatic ion, right? This is the cyclopentadiol cation, and this is cyclic. It's planar because there'll be a p orbital here, and so they'll all have to overlap, right? I can draw resonance forms for it. It has a contiguous pi system, right? Because there'll be a p, 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 p. But this only has 4 pi electrons, right? 2 in here and 2 in here. There are no pi electrons in this one. So this really is what's called a 4n system, which I'll get to in a second. So this is not aromatic, so I'm going to leave that as it's drawn. This is the cyclo-octa-triennyl dication. And I can draw multiple resonance forms for this, right? I can put the positive charge here instead, right? If I move that electron pair here, so it doesn't really matter how I draw it. So is that species aromatic? Cyclic, planar, which it have to be because it's pp and then p's all around. Contiguous pi system and 2, 4, 6 pi electrons. So this is an example of an aromatic cation. Or to be more precise, it's an aromatic dication. Okay, the last point I'll make is that there are 3 categories of compounds that we need to talk about. So compounds may fall into the set of being, I can either be non-aromatic, I can be aromatic, and I can be anti-aromatic. Okay. If I am neither, if I fail any one of these 3 tests, I am non-aromatic. So hexatriene wasn't cyclic. So hexatriene is a non-aromatic compound. End of story. The cyclohexadiennyl cation